Right now, more than 12 billion miles from where you are sitting, a machine the size of a small car is falling through absolute darkness at 34,000 miles an hour, and it has been falling for 49 years. It carries a golden record etched with the sounds of Earth, whale songs, a baby's cry, greetings in 55 languages, in case something out there ever finds it. Its power is dying, 1 watt at a time. Its instruments are being switched off one by one, like rooms going dark in a house nobody lives in anymore. And in July of 2023, NASA lost it completely. A single wrong command sent from a room in California tilted its antenna 2 degrees away from Earth, and just like that, humanity's most distant working machine went silent. A deaf and mute, still flying, still alive, but utterly unreachable, hurtling deeper into the void with nobody able to tell it to stop, to turn, to even say hello. What happened next involved something engineers called an interstellar shout, and whether it would work or not, nobody would know for 37 agonizing hours. This is the story of Voyager 2, the only spacecraft in the history of our species to have visited all 4 giant planets, the only one to have ever laid eyes on Uranus and Neptune up close, and the machine that, against every reasonable expectation of physics, a budget, and time, is still talking to us from beyond the edge of the solar system. To understand how strange and lucky this all is, you have to go back to the early 1960s, when a young engineer at NASA's Jet Propulsion Laboratory noticed something on a piece of paper that would end up shaping the rest of the century. He realized that in the late 1970s, the 4 giant planets of our solar system, Jupiter, Saturn, Uranus, and Neptune, would fall into a rare alignment that happens only once every 175 years. If you could time a spacecraft's launch just right, you could use the gravity of each planet to fling the next one closer, slingshotting your way across the entire outer solar system using a fraction of the fuel it would normally take. Instead of a mission lasting 30 years, you could do it in about 12. This kind of geometric coincidence would not happen again until the 21st century's opposite parent generation was long gone. Miss this window, and the next person to see Neptune up close might not be born for 2 more centuries. NASA's original plan was audacious to the point of reckless. They wanted 4 separate spacecraft, a full grand tour, 1 for each planet. But budgets in Washington do not care about rare planetary alignments, and the grand tour was slashed down to something far more modest on paper and far more ambitious in practice. 2 spacecraft, twin machines, each carrying 11 scientific instruments, a camera system capable of resolving details invisible from Earth, and just enough hydrazine fuel and plutonium power to maybe, if everything went right, survive long enough to see it all. They were named Voyager 1 and Voyager 2. And here's the first strange twist in this story. Voyager 2 launched first. On August 20th, 1977, from Cape Canaveral, Florida, Voyager 2 lifted off the pad atop a Titan Centaur rocket, 16 days before its twin sibling would even leave the ground. It sounds backwards, and it is, but the trajectories were designed so that Voyager 1 would take a faster, more direct path, and actually overtake Voyager 2 before either of them reached Jupiter. Voyager 2 was also built as an insurance policy. If Voyager 1 failed during its flybys of Jupiter or Saturn, mission planners were prepared to redirect Voyager 2 onto the exact same path, sacrificing any chance of reaching Uranus and Neptune, just to make sure humanity got at least one good look at the 2 closest giants. Nobody knew yet whether either spacecraft would survive the trip. The interplanetary environment beyond Mars was still largely a mystery, and there was a real, quiet fear inside Mission Control that radiation, micrometeorites, or simple mechanical failure could kill these machines before they ever got anywhere near their targets. They did not fail. And by the time Voyager 1 completed its successful data gathering at Saturn's giant moon Titan in November 1980, something had already been decided that would define the entire rest of both spacecrafts' careers. Titan was believed, correctly, to be one of the most scientifically important moons in the solar system, a world with a thick atmosphere, organic chemistry, and maybe even the ingredients for life. Mission scientists wanted a close, dedicated flyby, and the only way to get one was to bend Voyager 1's trajectory sharply upward, out of the flat disc-shaped plane in which all the planets orbit the Sun. It was the right scientific call. It was also a one-way door. Once Voyager 1 tilted out of that plane to study Titan, there was no physical way to bring it back down to encounter another planet ever again. Pluto had briefly been considered as a target, but the same math applied. You could not visit Titan and Pluto with a single trajectory, and Titan won. Voyager 1 would spend the rest of its existence flying up and out, or alone, into interstellar space, having completed its planetary tour after only 2 stops. Voyager 2 was not on that same trajectory. It had been sent on a slower, more patient path specifically, so that if both spacecraft succeeded at Jupiter and Saturn, it would remain free to keep going, deeper into the solar system toward 2 planets that had never been visited by anything humans had ever built, And once Voyager 1's mission at Titan was declared a success, the order came through. Voyager 2 was released. It would go to Uranus. And then, almost unbelievably, it would go to Neptune. To this day, it remains the only spacecraft in human history to have done either. Nobody has been back. Nobody has current plans, fully funded and confirmed, to return anytime soon. Everything we know about those two ice giants at a close range, we know because of one machine, one narrow trajectory, and one decision made in 1980 about a moon called Titan. But before any of that, there was Jupiter. Voyager 2 reached the giant planet in the summer of 1979, arriving a few months after its twin, and what it found rewrote the textbooks. Earlier missions, the Pioneer probes, had flown past Jupiter and reported a planet with a fairly static, unchanging atmosphere. Voyager 2 discovered the opposite was true. The clouds were roiling, shifting, alive with storms larger than entire planets. The Great Red Spot itself, a storm that had already been raging for at least a century, was seen drifting slightly, changing shape, changing color, breathing like something organic. And then there was Io, of everything Voyager found at Jupiter. Nothing shocked scientists more than this small, sulfur-yellow moon. As Voyager 1 was preparing to leave the Jupiter system, an engineer named Linda Morabito was examining a navigation image, checking star positions in the background, when she noticed something strange curling off the edge of Io's crescent. It looked like an umbrella-shaped plume rising hundreds of miles above the surface. It took a moment for the realization to sink in. Io was not just geologically active, it was erupting, live, on camera, the first time an active volcano had ever been observed anywhere in the solar system beyond Earth. When Voyager 2 arrived and got its own close look months later, it confirmed the volcanoes were still going, some of them changing entirely between the two visits. Plumes appearing and disappearing, the surface of an entire moon being repainted in real time by molten sulfur. Nobody expected this. A small moon squeezed and stretched by the immense gravity of Jupiter and its neighboring moons, heated from the inside by friction alone, turned out to be the most volcanically active body ever found, more active than Earth itself. Io was not the only moon that reshaped what scientists thought they knew at Jupiter. Voyager 2 swept in far closer to the icy moon Europa than its twin had managed, and the images it sent back showed a surface unlike anything else in the solar system. A smooth, cracked shell of ice, crisscrossed with long reddish lines like a cracked eggshell held together by tape. There were almost no impact craters, which told scientists something important. A surface with few craters is a young surface, geologically speaking, one that has been resurfaced recently, meaning something underneath is actively erasing the scars of old impacts. The leading explanation, still favored today, is a liquid ocean sitting beneath that icy crust, kept warm enough to stay liquid by the same gravitational squeezing that makes Io's volcanoes erupt. It would be decades before that idea moved from hypothesis to strong probability, but the seed of it, the very first hard evidence, came from Voyager's cameras in 1979. Further out, Ganymede, the largest moon in the entire solar system, larger even than the planet Mercury, revealed a surface split between old, heavily cratered dark terrain and younger, grooved bright terrain, evidence of ancient tectonic activity on a moon nobody had previously suspected of being geologically alive at all. And Voyager 2 discovered something Jupiter had been hiding entirely from view. A faint, dark ring system encircling the planet, invisible from Earth, confirmed for the first time in these flyby images, making Jupiter the second planet, after Saturn, known to wear rings. From Jupiter. Then at Voyager 2 continued outward, and in August 1981 it arrived at Saturn, following Voyager 1's path by about 9 months. Saturn's rings had fascinated astronomers since Galileo first pointed a crude telescope at them centuries earlier. But nobody, not even the scientists working on the mission, was prepared for what a close pass would reveal. What looked from Earth like a handful of simple, solid bands turned out to be thousands of individual ringlets, gaps, braids, and strange radial features nicknamed spokes that seemed to hover above the ring plane and rotate with the planet's magnetic field rather than with simple orbital mechanics, something that still puzzles scientists today. As Voyager 2 dove through the ring plane itself at 8 miles per second, it flew straight into a hail of microscopic dust particles, grains smaller than sand, but moving so fast relative to the spacecraft that they vaporized instantly on impact, creating tiny bursts of plasma. The impacts were strong enough to physically knock the spacecraft's orientation off balance over and over, forcing its control jets to fire automatically, again and again, just to keep the antenna pointed roughly toward Earth. For a few tense minutes, this multi-billion-dollar, one-of-a-kind machine was being pelted by what amounted to sand blowing through space at enormous velocity, and it survived. It photographed the moon Hyperion, an oddly shaped tumbling chunk of ice and rock, now nicknamed the Hamburger Moon for its strange, lumpy appearance. It got a close look at Enceladus, a moon so bright and reflective it seemed to be made of freshly fallen snow, a mystery that decades later would be explained by another spacecraft, Cassini, finding geysers of water ice erupting from Enceladus's south pole, evidence of a hidden ocean, but the seed of that discovery was planted here by Voyager 2's cameras in 1981. It photographed Tethys and its enormous canyon system, a scar stretching almost two-thirds of the way around the entire moon. It caught Phoebe, a small, dark, oddly colored moon orbiting backward and far out from the others, a world so different from its neighbors that scientists suspected, correctly, that it had not formed alongside Saturn at all but had been captured later, wandering in from somewhere else entirely, a distant cousin of the same kind of story that would later play out again, on a much grander scale, at Neptune. And it studied Titan's thick, hazy orange atmosphere from a distance, unable to see through the clouds to the surface, but confirming just how strange and promising this moon really was. Information that decades later would help justify sending an entirely separate mission, Cassini and its Huygens lander, all the way back to actually touch down on it. Then, for 8.5 years, Voyager 2 simply flew, silent and alone, carrying its data and its cameras across nearly 2 billion additional miles of empty space, aimed at a target nobody had ever seen up close, Uranus. Consider for a moment what kind of machine was actually making this journey. Voyager 2 was designed and built in the first half of the 1970s, using computer technology that, by today's standards, is almost laughably primitive. Its onboard computers had a combined memory measured in kilobytes, not gigabytes, a tiny fraction of the processing power sitting inside a modern calculator, let alone a phone. Every single command it would ever need to execute at Uranus and Neptune, encounters that would not happen for another 5 to 12 years after launch, had to be anticipated, written, tested, and in some cases physically reprogrammed from Earth, using radio signals sent across a gap so wide that a single message took hours just to arrive. Engineers back on the ground had to teach an aging spacecraft entirely new tricks mid-flight, rewriting its image compression software to squeeze more detail out of a weaker signal, adjusting its data transmission rate again and again to compensate for the ever-increasing distance, essentially performing open-heart surgery on a patient that was already billions of miles away and moving further every second. None of the original engineers who built Voyager 2 in the early 1970s could have guaranteed it would still be capable of any of this by the time it reached Neptune, and yet it was. Because a small dedicated team kept adapting the ground software and rewriting instructions for a machine that could not simply be updated the way software is today, a machine that had to carry, essentially, its entire future inside a memory smaller than a single low-resolution photograph. When it finally arrived in January 1986, the planet that greeted it was, at first glance, almost disappointingly calm. Pale blue-green, nearly featureless, a smooth ball of gas with none of the swirling drama of Jupiter or Saturn. But the real surprises at Uranus were not visible to the eye. They were hidden in the planet's physics. Uranus, unlike every other planet in the solar system, rotates almost completely on its side, tilted 98 degrees, essentially rolling around the sun like a ball instead of spinning upright like a top. Nobody fully knows why, though the leading theory involves a catastrophic collision sometime in the planet's early history, an impact violent enough to knock an entire world over. Voyager 2 confirmed this bizarre tilt firsthand, and then found something even stranger layered on top of it. The planet's magnetic field, the invisible bubble of magnetism that every planet with a molten metal interior generates, was not aligned with its axis of rotation at all. It was offset by 55 degrees, and it was not even centered on the planet. It was shifted dramatically off to one side. This meant that as Uranus rotates, its magnetic field wobbles through space like a poorly balanced spinning top, corkscrewing outward in a shape nobody had ever recorded before. Scientists are still trying to fully explain it today, decades later, and Voyager 2 remains the only source of that direct measurement because nothing else has ever gone back to check. And then there was Miranda, the smallest of Uranus's major moons, and by far the strangest object Voyager 2 photographed on its entire journey. From a distance, Miranda looked unremarkable, a small gray ball a few hundred miles across. But as Voyager 2 closed in for its flyby, sweeping past at a distance of just 17,000 miles, closer than any planetary encounter in the mission so far, the images that came back left scientists staring in confusion. Miranda's surface was a chaotic jumble. Giant grooved canyons running directly into completely different, unrelated terrain, cliffs of ice rising 12 miles high, higher than anything on Earth. sitting right next to smooth plains that looked like they belonged to an entirely different moon altogether. It was as if someone had taken several different worlds, shattered them into pieces, and then glued the fragments back together at random without bothering to match the seams. One leading theory suggested that Miranda really had been blown apart by some ancient impact and had reassembled itself under its own gravity. A moon that quite literally died and came back together wrong. The project scientist working on the mission would later say that this discovery taught them a moon could look like almost anything, that nature had far more imagination than any of their models had accounted for. Nobody had expected a small, otherwise unremarkable ice ball to become one of the most geologically bizarre objects ever photographed. Voyager 2 also found new moons at Uranus, 10 of them previously unknown, invisible from Earth, hiding in the planet's shadow in its faint ring system. It discovered 2 new rings in addition to the narrow, dark ones already known, confirming that Uranus, like Saturn and Jupiter, were a system of debris around it, just fainter and harder to see. And then, its work at Uranus complete, having spent less than 6 hours at closest approach after a 9-year journey to get there, Voyager 2 aimed itself at empty space once again, this time toward the very edge of the known solar system, toward a world so distant that even in 1986, astronomers were not entirely certain what they would find when they got there. 3.5 more years passed. On board, engineers back on Earth were quietly working miracles just to keep the spacecraft's cameras functional this far from the sun, this far from any light. Neptune orbits nearly 3 billion miles from our star, receiving sunlight roughly 900 times fainter than what reaches Earth. Taking a clear photograph out there required exposure, times measured in many seconds, which is normally impossible for a spacecraft hurtling through space at tens of thousands of miles an hour, since the smallest motion blurs the image into a smear. Engineers solved this by programming the entire spacecraft to slowly rotate during each exposure, precisely counteracting its own motion, essentially performing a controlled pirouette millions of miles from home just to take a sharp picture. It worked. On August 25th, 1989, Voyager 2 made its closest approach to Neptune, passing just under 3,000 miles above the planet's cloud tops, the tightest flyby, distance of the entire 12-year mission, deliberately threaded through a gap in the ring system that mission planners hoped, and confirmed only afterward, contained no debris large enough to destroy the spacecraft in an instant. What Voyager 2 found at Neptune stunned everyone watching. This was a planet so far from the sun that theoretical models predicted it should be a nearly dead, frozen, motionless world. Too cold and too starved of solar energy to have any real weather at all. Instead, Voyager 2's cameras revealed the most violent winds ever measured anywhere in the solar system. Sustained speeds of roughly 680 miles per hour, faster than the speed of sound, ripping across a planet that receives less than 1,000th of the sunlight Earth does. Nobody had a good explanation for where all that energy was coming from. There was a colossal storm system nicknamed the Great Dark Spot, roughly the size of Earth itself, a swirling anticyclone punching through Neptune's blue methane atmosphere, and beside it, a smaller, fast-moving white cloud that engineers nicknamed Scooter for how quickly it raced around the planet. 4 faint rings were confirmed, along with 6 previously unknown moons discovered in the images as they streamed back to Earth. But the single most haunting discovery at Neptune was not the planet at all. It was its largest moon, Triton. Triton is unusual from the very start, because unlike almost every other major moon in the solar system, it orbits Neptune backward, moving in the opposite direction of the planet's own rotation. This kind of retrograde orbit is a strong sign that Triton was not born alongside Neptune the way our own moon was born alongside Earth. Instead, it was very likely captured, a wandering object from far out in the Kuiper Belt that drifted too close to Neptune's gravity one day, billions of years ago, and never left. Some scientists have gone further, suggesting Triton may be a close cousin of Pluto itself, essentially a dwarf planet that got kidnapped by a gas giant, which makes the timing almost poetic, since Voyager's original planned route in the 1970s would have sent it to Pluto directly, before mission planners chose Titan instead. In a strange way, at Triton, Voyager 2 got to see a Pluto-like world after all, just wearing a different mailing address. And what it found there was extraordinary. Triton is one of the coldest measured objects in the entire solar system, its surface hovering around negative 390 degrees Fahrenheit, cold enough that nitrogen itself freezes solid. And yet, despite that unimaginable cold, Voyager 2's cameras captured something moving on the surface. Dark streaks of material stretched out across the frozen ground by high-altitude winds, sourced from geysers erupting directly out of the frozen crust, shooting nitrogen gas and dark dust particles miles into Triton's thin atmosphere before the wind carried them sideways and let them settle back down. Ice volcanoes on one of the coldest, most distant objects ever observed up close. It remains, to this day, The last time in human history that a spacecraft encountered a genuinely new, previously unvisited world for the very first time, a distinction it held for over a quarter of a century until New Horizons finally reached Pluto in 2015. With Triton behind it, Voyager 2's planetary tour was officially over. 12 years, 4 planets, 16 new moons discovered, rings found around 3 worlds that were not known to have them before the mission began, and images and data that rewrote entire chapters of planetary science textbooks. And then, having done everything it was originally built to do, the spacecraft simply kept flying. There was nothing left to stop it. No more planets in its path, no more scheduled encounters, just open space and momentum, carrying it further from the sun with every single second. It became, in essence, a permanent scientific outpost, its remaining instruments repurposed to study the outer reaches of the sun. As influence, the giant invisible bubble of charged particles called the heliosphere that surrounds our entire solar system, like a bubble surrounds a swimmer underwater. For nearly 3 decades after Neptune, Voyager 2 traveled through this bubble, sampling the thinning solar wind, watching the sun's magnetic influence slowly fade with distance. And then, on November 5th, 2018, instruments on board detected an abrupt, unmistakable change. The density of charged particles jumped sharply. The direction of the surrounding magnetic field shifted. Voyager 2 had crossed the heliopause, the true boundary of our solar system, the place where the sun's influence finally gives way entirely to the empty space between stars. It became only the second human-made object in history to reach interstellar space, following its twin, Voyager 1, which had crossed that same boundary 6 years earlier in 2012, at a completely different location and a completely different time. Scientists got something unique out of Voyager 2's crossing that they never got from Voyager 1, because unlike its twin, Voyager 2 still had a working plasma instrument on board, a piece of equipment that had failed on Voyager 1 years earlier. For the first time, researchers could directly measure the density and temperature of the material outside our solar system as a spacecraft actually crossed into it, not inferred, not calculated, but measured, live, in real time, from more than 11 billion miles away. Both spacecraft are still out there today, drifting further from home every single second, each carrying an identical copy of the Golden Record, a phonograph disc plated in gold, designed to survive essentially unchanged for over 1 billion years in the vacuum of space. On it, mission scientists and a committee led by the astronomer Carl Sagan compiled a sound and image portrait of an entire planet. Greetings, recorded in 55 different human languages. Whale calls, thunder, footsteps, laughter, a mother's kiss, music spanning cultures and centuries, and images encoded directly into the grooves, showing everything from human anatomy to city skylines to the structure of DNA. Instructions for playing it are etched onto the record's cover in symbolic diagrams, on the theoretical chance that some future intelligence, human or otherwise, might one day find this drifting artifact and wonder what it was listening to. Neither spacecraft was designed to be found. The odds of that happening are astronomically small, but the decision to include the record anyway says something about the people who built these machines, that even while chasing hard science, magnetic fields, and ring particles and atmospheric pressure, they also built in a small, deliberate act of hope. See it reach even its first distant star, launched during a decade when the idea of a personal, and then, in the summer of 2023, that hope nearly ended in silence. On July 21st, engineers at NASA's Jet Propulsion Laboratory sent a routine series of commands to Voyager 2, part of a scheduled sequence meant to adjust the spacecraft's systems. Somewhere in that sequence, an error crept in, and instead of the intended instructions, the antenna was told to rotate just 2 degrees away from Earth. 2 degrees does not sound like much. On a road, it would barely register as a wrong turn. But at a distance of over 12 billion miles, a 2-degree error in the direction a narrow, focused radio beam is pointed is more than enough to send that beam missing Earth entirely, vanishing off into empty space instead. Voyager 2 went silent. Not broken, not lost, not damaged, simply unreachable, still flying its programmed course perfectly, still gathering data exactly as instructed, but with no way to receive new commands and no way to send its findings home. It was the longest communications blackout in the entire history of the mission. For days, all NASA's Deep Space Network could detect was a faint carrier signal, essentially a heartbeat with no words attached, confirmation that the spacecraft was alive but nothing more. The official recovery plan involved simply waiting. Voyager 2 has an automated failsafe programmed to reset its orientation and repoint its antenna toward Earth several times a year regardless of outside instruction. And the next scheduled reset was not due until October, more than 2 months away. 2.5 months of silence from a machine already operating on fumes of power, already this fragile, felt like an unacceptable risk to wait out. So the team tried something bolder. On August 2nd, engineers at the Deep Space Network's Canberra, Australia facility aimed one of their most powerful transmitters directly at the last known position of Voyager 2 and sent out an extraordinarily high-powered signal, informally nicknamed among the team an interstellar shout, a burst of radio energy strong enough, they hoped, to be detected even by an antenna that was not properly pointed at Earth. Because the spacecraft is so far away, a radio signal traveling at the speed of light takes 18.5 hours just to reach it. Then, if the command worked, it would take another 18.5 hours for any response to travel back. 37 hours total of pure uncertainty, no way to check progress, no partial updates, just silence and waiting. At around 12:30 in the morning Eastern Time on August 4th, telemetry data began flowing back into mission control. It had worked. Voyager 2, 46 years old at the time, more than 12 billion miles from the room where a handful of engineers had just spent 2 weeks anxiously refreshing displays, had heard a shout across interstellar space and turned itself back around. The spacecraft is not invincible, and everyone working on the mission knows it. Both Voyager probes run on radioisotope thermoelectric generators, devices that convert the natural decay heat of plutonium-238 into electricity. That power source has been quietly weakening since the day of launch, losing a small percentage of its output every single year, with no way to refuel it, no way to repair it, ever, from a distance of billions of miles. To compensate, mission engineers have been forced into an ongoing, decades-long triage, deliberately switching off one instrument after another, sacrificing pieces of the spacecraft's scientific capability in order to keep the remaining instruments and the all-important radio transmitter alive just a little bit longer. Heaters have been turned off on instruments that were never designed to function in temperatures this cold, and against all engineering predictions, they have kept working anyway. Every additional year of operation at this point is considered a bonus nobody promised, an extension purchased through careful power budgeting, and frankly, a fair amount of luck. Mission scientists have openly said they do not know exactly when. Either spacecraft will finally go dark for good, whether it will be a sudden failure or a slow fade into unreachable silence, only that the day is coming sometime in the years just ahead, and that when it does, it will mark the end of the longest continuously operating spacecraft mission in human history. But even after that last signal fades, even after the transmitters finally fall silent and mission control shuts down the receivers, Voyager 2 does not stop moving. It cannot. There's no friction in the vacuum of deep space to slow it down, no atmosphere to burn it up, nothing to stop its forward momentum except the almost imperceptibly weak pull of gravity from stars it has not even reached yet. It will keep drifting, silently, forever, or as close to forever as anything built by human hands can manage. In roughly 40,000 years, a span of time longer than all of recorded human civilization stacked several times over, Voyager 2 will pass within about 1.5 light years of a small, dim red star called Ross 248, currently sitting in the constellation Andromeda. It will not stop there. It has no engines left to slow down, no way to enter orbit around anything, so it will simply continue on, sailing past that star system the way it sailed past Neptune, a fleeting visitor, and keep going. Long after that, hundreds of thousands of years from now, it will drift near other stars entirely. Sirius, the brightest star in Earth's night sky, among them, each encounter nothing more than a distant, silent flyby, watched by no one, recorded by nothing. Because by then, every instrument on board will have been dead for hundreds of thousands of years. It will just be a piece of metal, gold-plated record still attached, tumbling gently through the galaxy, technically still moving on the same trajectory NASA engineers plotted for it on paper back in the 1970s. There is something almost unbearably strange about that fact, when you actually sit with it. Right now, today, that machine is out there. This exact moment, continuing to move, continuing to carry a message nobody may ever receive, built by people who will not live to.